Okay, so the next thing we need to talk about is a little bit more information about the electronic structure within atoms. It turns out that electrons exist in energy levels. Which we usually abbreviate as N. And the N can equal any integer greater than or equal to 1. So an electron can exist in n equals 1, which we would call the first energy level. It can exist in the second energy level, the third, the fourth, and so on. Within the energy levels, electrons also exist in what are known as orbitals. Okay, we've got letter designations for the sublevels which orbitals are in. They are S, P, D, and F. S, P, D, and F. The amount of s orbitals, the amount of orbitals within the particular sublevels changes. Turns out that the s sublevel only has one orbital, the p sublevel has 3, d has 5, and f has 7. Now that's going to be important because when we talk about how many electrons are within an individual energy level, we have to know how many electrons can, or how many orbitals are within those energy levels, and of course how many electrons can fit in those orbitals. Each orbital can hold 2 electrons. And that has to do with their spin. It's a magnetic spin. This electron can be spin up or spin down. And so that's why each orbital, or it's one of the reasons why each orbital can hold 2 electrons, one that's known as spin up and one that's known as spin down. But for right now, that's not really all that important. What we do need to know is that the first energy level only has an s orbital. And so, if you think each orbital can hold 2 electrons, and there's only one orbital in the s sublevel, which we call the s orbital, only 2 electrons can exist in the first energy level. If n equals 2, we've got the second energy level. Electrons actually can exist in the s orbital or the p orbitals, all 3 of them. Okay, so in the second energy level, there's s and p orbitals, and since the p sublevel has 3 orbitals, each orbital can hold 2 electrons. That means there could be 2, 4, 6, 8 electrons in the second energy level. And then the third energy level has s, p, and d orbitals. And then again, 2 electrons in each orbital for a total of 10, 6, and then 18. And then finally, n equals 4, can have s, p, d, and f orbitals. And if you do the math, we've got 14 electrons here, 10, 8, and then 2 more. That's a total of 32 electrons that can be held in the 4th energy level. If you remember back, thinking back to the periodic law that set up our periodic table, that is what determines the periodicity for the periodic table, or the periodic law, excuse me. The periodicity changed from 8 to 18 to 32. Okay. For the most part, well, we're just going to have to deal with the first 3 energy levels, and for the most part, the elements that are the most important in this course primarily only have electrons in the s and p orbitals. A good way to figure out how many electrons each energy level can hold is that there's a simple equation: number of electrons equals 2n squared. Whatever energy level you're in, square it, and then multiply by 2, and that will give you the 2, 8, 18, or 32 numbers. Okay, so what we want to do is determine what are known as electron configurations, or write out electron configurations for the elements. Okay, and what we have to do is we have to put electrons into the different energy levels and sublevels and orbitals in order of increasing energy. What we want to do is start putting electrons in the lowest energy first. That is because they are the most stable there first, initially. Okay, so the first orbital is the 1s. The second orbital is the 2s. And then there's the 2p orbitals, which can hold 6 electrons, 2 in each orbital. And then there's the 3s with 2 additional electrons. Next is the 3p with another 3 orbitals, can hold 6 electrons. And finally, for our discussion, we'll stop at 4s for now. Okay, so what we're going to do is we're going to identify the electrons and what orbitals they're in for each atom. Okay, so the first one is pretty easy. Hydrogen has 1 electron, and it's going to go into the 1s orbital. So how we write electron configurations is we write the energy level as its integer value, and then we show how many electrons are in the sublevel by writing down the letter designation for the orbitals, and then as a right superscript, show how many electrons are in that orbital. So the first, hydrogen, has 1 electron in the n equals 1 energy level and s orbital. The next element, helium, has an electron configuration of 1s2. Its first 2 electrons go in the 1s orbital. We can keep going like this, but eventually we're going to have to put electrons into different energy levels and orbitals. Lithium has 3 electrons. First 2 have to go into the 1s2. Only 2 electrons orbitals can only hold 2 electrons, so the third electron has to go into the 2s. So we'd write that electron configuration as 1s2, 2s1. And we'd keep going like that, filling up the electron configurations, eventually having to put electrons into the 2p orbitals. One thing that can help us write electron configurations is to look at the periodic table. It has some very specific regions that sort of pop out at you. If you notice over here, there's these 2 rows that sort of pop out, and then over here the rest of the main group elements have 6 rows that sort of raise above, and there's 10 groups in the middle between those 2 areas. And then down here, there's another 14 elements. If you think back to our orbitals and the number of electrons that I'll sneak in right here in each sublevel, S can hold 2, P can hold 6, D can hold 5 times 2, 10, and F can hold 7 times 2 is 14. That is what explains the different regions of the periodic tables. We'll often call this region right here the S block, because electrons going to those atoms are in the s orbitals. The 6 rows over here we'll often refer to as the p block. The 10 groups in the middle of those 2 areas are called the d blocks, because when those elements get electrons, they're putting them in the d orbitals. And then down here, these 14 groups is known as the F block, because these are the first elements to get F electrons. Okay, so the way I use the periodic table to figure out electron configurations is to put put electrons for each element, and then wherever I'm at in the blocks, I know that those electrons are going into that specific orbitals, those specific orbitals. The only thing we have to remember is that helium electron is a 1s electron, so really, for electron configuration purposes, helium should be over here. Of course, it's over on group 8A or 18 because it is a noble gas and shares the same chemical and physical properties as the noble gases. Electron configurations is actually why hydrogen is over here. Hydrogen is a non-metal, even though it's on the left side of the periodic table with the other metals. It sits in group 1 because of primarily its electron configuration and its propensity to form a +1 ion. It makes a lot of sense to put it there. Okay, so when I'm writing an electron configuration, let's say I want to write the electron configuration for carbon. I'm going to follow the periodic table, placing electrons either in the s or p orbitals, and the energy level will correspond to the period that I'm in for s and p orbitals. So my first electron is in the 1s orbital, and the second one is also in the 1s orbital, so there's 2 there. Now I've ran out of periodic table, I have to come down to the second row, so now I am in period 2, so my energy level is 2. I'm in my s block again, so it's 2s1, 2s2. And I keep on doing this until I hit the element that I want. So 2s1, 2s2, now I have to come over here to the p block. I'm still in n equals 2, so this is 2p1, 2p2, and I've hit carbon. So that's carbon's electron configuration. 1s2, 2s2, 2p2. One way you can double check this is that the number of electrons should add up to its atomic number if it's a neutral atom, because the atomic number is number of protons. If it's neutral, that's its number of electrons. So a carbon atom should have 6 electrons, and it does 2, 4, 6. Let's do a little bit harder one. Let's do phosphorus, all the way to phosphorus. So this was the electron configuration for carbon. The electron configuration for phosphorus would start out the same way. 1s1, 1s2, if I want to use helium over there. We come down to the second period, so it's 2, 2s1, 2s2, just like carbon. And I keep on going, just like carbon. 2, I'm over in the p block, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 2p6. If I was looking for the electron configuration for neon, I'd be done. Electron configuration for neon is 1s2, 2s2, 2p6. But I'm going after phosphorus, so I've hit the end of the periodic table. I have to come down here. Now suddenly I am in period 3. So that's going to tell me that I'm in energy level 3 for my electrons. I'm back in my S block, so it's 3s1, 3s2. And I have to travel all the way over to my P block. So now it's 3p1, 3p2, 3p3, 3p4, I wanted to go after phosphorus, so I'm done. 3p1, 3p2, 3p3, 3p3. The electron configuration should add up to 15. That's how many electrons a phosphorus neutral atom would have. So 2, 4, 10, 12, 15. And that is correct.